This is a classical example. It's a cantilever beam which is deflected as a result of electrostatic forces. Again, this is an electrical and mechanical systems interaction, and they are bidirectionally coupled with each other then. What you see in this model is a cantilever beam which is made out of polysilicon. It is fixed at one end, but otherwise it is actually free to move the way it wants to displace itself. And the lower side of this beam is actually coated with a metallic layer which will act as one of the electrodes then. And the beam is surrounded by some volume of air which is represented by a rectangular box around this beam. And if you look at the simulated result on the right side of the screen, you can see that I've actually hidden some of the boundaries so you can actually visualize what's going on the inside then. The bottom surface of this air box or the air volume is grounded, and then an electrical potential is applied to the lower part of the beam, which actually has a metallic layer as an electrode. And because of the potential difference between the applied potential and the ground, the beam will start to bend. Once this bends, there will be a change of geometry in the air, and also there is an electrical field change between the two electrodes. Again, in this case, because there are moving geometries, moving mesh in COMSOL is used to take this into account, to accurately calculate the values of, say, capacitances if you wanted to. In COMSOL, it is also important to note that you can parameterize on any variable that you want, including the dimensions of the geometry itself. In this case, the voltage is basically varied from all the way from 1 volt to 6.1 volts. If you look at the left-hand side of the slide, there is actually a plot which basically looks at the displacement along the x direction for different voltages, going from 1 to 6.1 volts. As the voltage increases, the displacement increases. Because of the change in volume between the two electrodes, which is of course a result of the beam movement itself, the capacitance is going to change, which you can of course plot, which is the center plot that you see in the slide then. And you can also do frequency response analysis, so you can do AC analysis. You can calculate the AC capacitance, or basically the impedance value also. And this is what is shown on the rightmost plot in the screen. So lumped parameter characterization is actually very, very easy in COMSOL. And things which are also very important in MEMS applications, one of them is film damping. How would you include film damping in the MEMS module, for example? Let's take a MEMS gyroscope. This device is entirely built from a single piece of polysilicon, which basically polysilicon includes is used to make the proof mass, the support structure, the driving units, and everything. And in a gyroscope, what happens is when the drive mode is excited, let's say it could be tangential or of course orthogonal to the surface, then the distance between the sensing electrodes and the proof mass actually changes. And the distances or the gap between the sensing electrode and the proof mass are usually very, very small, and they're usually filled with some kind of a gas or maybe even just air. In this case, the model assumes that there is an air gap between the sensing electrode and the proof mass. And this is going to cause damping. And this model is basically used to find the effect of damping on the Q factor of this device or this gyroscope. Remember that in this model, all other damping mechanisms, say the intrinsic damping and things like that, are assumed to be extremely small, and therefore just the damping caused by the air film is included in this model. Okay, of course, if you wanted to, you can add other damping mechanisms as well. The film damping is included in the simulation through a special interface specifically available for this purpose. This is shown at the bottom left of your screen, with a red box around it where you include the parameters which are essential for film damping. You can include the initial film thickness, you can include the dynamic viscosity, and things like that. When the distance between the proof mass and the sensing electrode changes, the capacitance changes because the electrical field is changing. You can actually calculate that. That's again a lumped parameter characterization. In this model, a frequency response analysis was done, so you can calculate the Q factors, which is basically shown from the calculated from the plot that is there on the rightmost side of the screen. Once this is calculated, then film damping is used, which is basically fluid damping on the underside of the device then. Once film damping is included, you can actually see the variations in the Q factor, and you can actually calculate the effect of film damping then. So this is used in many, many MEMS applications then. So we can now move on to something slightly more different. COMSOL's MEMS module can also model piezoelectric devices, which are electromechanical in nature. Within this field, you can model, say, transducers, actuators, sensors, filters. This is a completely vast area by itself, and all of this is included in the MEMS module. In this slide, I've just shown you a bunch of different examples, one being a micro gripper, which is basically, if you really look at it, the comb drive example was used for also a micro tweezer kind of an application. This is very, very similar, but in this case, the actuation is basically a piezoelectric actuation. So you can even do contact analysis. You can see that the tips of the micro gripper actually come in contact with each other. So you can calculate contact forces if you wanted to. You can model even quartz crystal monitors based on say 80 cut quads and things like that. You can radially polarize your device and things like that. In the next slide, I will show you some of the features, or basically the user interface for modeling piezoelectric devices. When it comes to piezoelectric modeling, there are a couple of important things to note. One is the material properties, and then the orientation of the materials. These things become extremely critical. COMSOL has at least 23 different material properties which are built in for piezoelectric materials. You have all the classics, which are basically lead zirconic titanate with various combinations. These are all Navy type materials. Then you have lithium niobate, lithium tantalate, quartz. I haven't shown the entire list here, but there are approximately 23 different materials which are pre-built. And on top of this, the user interface also allows you to define your own material properties. You can specify material properties both in the strain charge or in the stress charge. In most cases, you can basically take these properties directly from literature or from, say, specification charts which a vendor might provide you with. You can just take the values right out of those data sheets and just type it in. You can even make them frequency dependent properties if you wanted to. And most of the other classical properties are already included in the material library. And with piezoelectric materials, the other thing is basically the material cut angles, which are also very critical because they determine the wave propagation direction. And COMSOL makes it very, very easy to define your own coordinate system through an Euler angle representation. Most of these materials with different cut angles have their own Euler angle representation. So you can look it up in the literature and just type it in the user interface, and you can make those in the simulations. So it's as easy as that. And even with piezo modeling, the MEMS module lets you perform stationary analysis. You can do transient analysis. You can do modal or Eigel frequency analysis to calculate the resonant frequency. You can also do frequency response analysis. So yes, even here you can calculate admittances, impedances, all your parameters as well. Okay. That being said, COMSOL's MEMS module also gives you an external circuit link. This is basically for including circuit elements to your model. Let's say you are interested in modeling a resonator's physical characteristics. If you want to build an oscillator around it, this can actually be done very, very easily. You model the resonator using this module, then you connect this model to an external circuit to simulate the complete oscillator with a feedback loop. The user interface lets you do this by either creating a circuit using the components which are provided in the user interface, which I have shown in the left-hand side of the screen, which is basically resistors, capacitors, inductors, some diodes and transistors and things like that. You can use those and build your own circuit, or what you can do is you can also import a SPICE circuit and then connect it to your model. The importing of a SPICE netlist is actually very, very simple. You can see from the left side of the screen that there is actually a choice to import a SPICE netlist. All you need to do is click on that, import your SPICE netlist, and then connect it to your circuit. And I have shown a very, very simple example on the right side of the slide. In this particular example, you can see that there is actually a cantilever beam with two piezoelectric elements, and it's connected to some kind of an external circuit where you have some resistors, some inductors, and of course there's a ground and some kind of an applied potential. So the external circuit basically drives the cantilever beam at different frequencies then. And as I had mentioned earlier, you can actually parameterize anything in COMSOL. So you can take this value of the inductor and give it different values so you can get different resonant frequencies.